A2 Maths, Proof by Contradiction. So last year you looked at a couple of different proof techniques. We're going to build on that by looking at what's called proof by contradiction. Now, proof by contradiction is exactly what it says. If you're given some sort of statement that you're trying to prove, so you're trying to prove this and this for a statement, the first thing you do is you assume that that given statement is not true. You want to contradict it. So whatever the proof is, you say, no, I don't believe that. I don't think it's true. And then what you try to do is, instead of trying to prove the initial proof, you try to show that your assumption that it's not true is impossible. So by showing that it's not true is impossible means it has to be true. So that's what we mean by proof by contradiction. We take an initial statement, we say it's not true, we show that it not being true is impossible, so therefore it must have been true. Okay, so to continue in your notebooks then, please, just write down this question. It's quite an important question because if you can understand how you do this one, you should be able to understand how you do any of these types of questions. And you need to look at learning this off by heart. So we'll go through this one relatively slowly, but make sure you've got it nice and clear in your notebooks, because for most of you just want to learn through each of those steps. Okay, so I want to prove by contradiction that root 2 is irrational. So because I'm using proof by contradiction, the first thing I say is that root 2 is rational. It's the opposite to what it's saying. I want to show that root 2 is a rational value. Okay. Now by rational, what rational means is that we can write it as a fraction. And what we mean by irrational is that you can't write it as a fraction. So for example, the number pi can't be written as a fraction. Whereas some other numbers that keep going, for example, 0.99999 can be written as a fraction. They are rational numbers. And we're trying to show that root 2 is rational. Right, so the first thing I want to say is that if it is rational, it means it can be written as a fraction, a over b. And what I make sure I'm aware of is that a and b are the simplest possible form. So I'm writing root 2 in the form a over b, where a over b is the simplest possible form of that fraction. In other words, a and b have no common factors. So an example of that could be that a equals 1 and b equals 2. Therefore, it's a half. What you wouldn't have is a equaling 2 and b equaling 4, because they have a common factor. It's not the simplest form. Okay, so my statement has to be to that effect. And of course, any fraction can be written down into its simplest form. Okay, so now I've got that statement started off. What I'm going to do is I'm just going to play with this statement, because this is what I'm assuming to be true. Okay, and I want to show that this just isn't true. It's impossible. So what do I do first? Well, I could rearrange this, couldn't I? I could certainly rearrange it by taking the b over to the other side. Okay, so b times root 2 must equal a, if that is true. I could also get rid of that root 2, couldn't I, by squaring everything. So if I square everything, the root 2 goes to 2, b squared, a squared. So I've got that. Then once I've got that, what that means is that if it's a number 2 on the front of it, it shows that a squared must be an even number, because even numbers by definition are 2 times something. All right, so any even number can be written as you know, 2n, 2 times a number. So a squared is 2 lots of b squared. It doesn't matter what b squared is, even if b squared is something like 9. 2 lots of 9 is still going to be 18, which is even. Okay, remember that a and b are natural numbers, so they are going to be numbers that you can, not decimals. So a squared must be even. So once I know that, I also know that a has to be even, because the only way you're going to get a squared number to be even, it means that a itself has to be even. All right, because obviously a squared could be odd, but the only way that's going to be odd is if you had an odd number put in. For example, 3 squared is 9. Okay, if it's even, a must be an even number. Okay, so I've got down to that fact. Just rearranging it, I've squared it, I've realised there's a 2 there, and 2 times the number makes it even. So therefore I've come down to the conclusion that if this is true, then a must be even. Now if a is even, that means a can be written in a different form. A can be written as an even number. And we know, right, from your GCSE skills and when you did proof last year, that an even number can be written as 2n. So we can write an even number as 2n. Right. So I know that a is even. I can write a as 2n. So what I'm going to do now is I'm going to replace a back into this formula. So I know that a is 2n. It's definitely an even number. So if I replace a for 2n, I get this. I can expand that, can't I? I can get 4n squared. And what I come down to is this conclusion just now. Once I divided by 2, I've realised that b squared equals 2 lots of n squared. And for the same reasoning that I did here, for exactly that same reasoning, I know now that b squared itself must be an even number. So therefore, b is an even number. Now, I won't write it as 2n. I'm going to write it as a different even number, 2m. But what I know now is that A and B have got to both be even if this is true. If this is true. Okay, so what does that mean then? Just because those two are even, does that mean that this can't be true? Well, it's back to this fact just here. One of the reasons why we wrote it like this is we said in our statement, A and B have no common factors. A and B are, A over B is the simplest form. A and B have no common factors. Now look at this now. Now that we've got down to this conclusion that A and B is in its simplest form, this is where the contradiction comes in. We notice that the square root of A over B, A is going to be 2n and B equals 2m, but that is a direct contradiction to what we said at the start. We said at the start that A and B have no common factors, but they clearly do. They both have a number 2 in common. So A over B is not the simplest form. N over M was the simpler form than that. So it breaks this assumption that we started with. So therefore, this is not true. Therefore, our assumption is not true, that we said it's going to be rational. So therefore, it's not rational. It must be irrational. So those steps that you can see there can work for lots of different square roots. You could do exactly the same sort of proof with the square root of 3 to prove that square root of 3 is going to be rational, and so on. You can also do it for cube roots as well. But learning these key steps, making sure you assume it's rational, writing it as a bit of algebra, trying to rearrange it to show that actually it's not in its simplest form, is exactly the same steps that you will use to prove any of these types of questions. So try to learn those key steps. Change it to algebra, show that it's not in the simplest form. Make sure you write that statement down that A and B have no common factors, or A and B in the simplest form. Okay, and make sure you use it by proof by contradiction. Okay, make sure you've got done what you need. Okay, so what we're going to look at is we're going to look at the proof that there is more primes than the first 6 prime numbers. Now, clearly you know that's true, right? You know there's more than the first 6 prime numbers. And we're not going to look at this with proof by contradiction just yet. We're going to use last year's skills just to show you that you don't have to just use proof by contradiction because it's a new skill. You can use some of your previous knowledge as well. So we're going to look at proof by counterexample. So proof by counterexample was a proof where you just have to find one example to show it's not true, and therefore you've proved it. Now in this case, we know that there's more primes than 2, 3, 5, 7, 11 and 13. Clearly 17. Right? You could take 17, you could divide it by 1 through to 17 and show that it's definitely prime. The reason why I'm just doing this extra technique though is not just to show you that you don't have to do proof by contradiction in all cases, but it's also just to look at some techniques on how to solve these sorts of questions as well. Okay, so just hopefully practicing what you did last year, but also just a reminder if or to teach you it if you didn't cover it last year. So the prime I'm going to pick though, bizarrely enough, is not going to be as easy as 17. I want to choose 211. I know that 211 is prime. So this question could have been done slightly differently. And this is the reason why I'm doing this. I could have wrote here, prove that 211 is prime. Okay. Now the problem with 211 is that you might be thinking, I'm not going to do that because I have to do divide by 1, divide by 2, divide by 3, and so on, all the way up to 211. It would take me ages. Okay, so you might be thinking that it just takes up too much work. So what I'd like you to do is think, do you have to divide by all those numbers? Is there some numbers that there's no point in dividing by? Okay. Well, the first thing you might think is actually there's no point in dividing anywhere past 105 or 106, that sort of region. Because I know that once I go past 106, it's definitely not going to be a factor past 106 because once I double it, it goes past 211. So there's definitely no factors that are past 106. So you might be thinking like that. You might also be thinking there's no point in dividing by the even numbers because I know you can't divide by 2, so therefore you can't divide by 4, 6, 8, 10 and so on. So there's ways of cutting down the sorts of numbers that you need to divide by. Okay, once you know it doesn't divide by 2, it certainly doesn't divide by any multiple of 2. Okay, that's the key thing. Right? If you know it doesn't divide by 2, you can't divide by any multiples of 2, but that's also true for 3. If you can't divide it by 3, there's no point in trying to divide any multiples of 3, like 6 or 9, because if 3 doesn't go into it, 9 definitely doesn't. Okay, but then that still causes a problem because you're still going to have to try all the numbers up to, let's say, 106, but you don't. The halfway point of that number is 211 is roughly 105, 106, but that's not the halfway point when we're thinking of these factor pairs. When you think of what two numbers times together to make 211, okay, the midpoint is the square root of it. So you don't need to try all the factors from 1 to 211. You only need to check up to the square root of 211. Because once you pass the square root, you've passed the point where you are going back on yourself. Okay, you are checking to pass them. I'll give an example. When you're looking at the factors of 12, you could say 12 divided by 3 is going to be 4. So 3 is clearly a factor, but so is the result of that, which is 4. So there's no point in checking 4 because you know its factor pair is 3. So you only need to go up to the square root of that number. So if I know the square root of 211, it's about 4.5. So there's no point in checking any numbers past 14.5. There's no point in checking them at all. If you've checked all the numbers before it, then there's no point in checking any numbers past it. Okay, so that makes it a lot easier. Now it's more manageable, isn't it? We only have to check the numbers 1 to 14. And if you decided just to check all the numbers from 1 to 14, then that's doable and you'll get the marks because you are showing it. But even then, you don't need to check them all. You don't need to check them all. We just said we don't need to check all the even numbers, apart from the first one, 2. We don't need to check all the multiples of 3, apart from the number 3. We don't need to check all the multiples of 4 because of 2. We don't need to check all the multiples of 5, once we've shown for 5. So in fact, you only need to check the first prime number, the prime numbers between 1 and 14. We only need to divide by these. If 211 doesn't divide by 2, 3, 5, 7, 11 and 13, it must be a prime number itself. So we can show that it's not divisible by 2, 3, 5, 7, 11 and 13. You can go through, you can check it. It's definitely not divisible by each of those. So therefore, if it does not divisible by each of those, 211 must be prime number itself. Okay, so write down the same question, but this time we're going to look at doing it with proof by contradiction. Okay, and the reason why I'm doing it again, you might think, oh, I've just done it, I'm not going to do it again. The reason why you're going to do it again is because this builds on the actual proof that there is an infinite set of primes, and that's a proof you need to learn off by heart. So we're going to look at proof by contradiction for this. So the first bit of the proof by contradiction we're going to say is we're going to assume that that's true. There is only 6 prime numbers out there. That's the only prime numbers we have. That's what we're going to assume is true. And what we're going to do is hopefully prove that that's not true, so therefore we prove that there is more. So if that's true, then what we can do is we can say there's no other primes out there at all. And what we'll do is we'll write a prime number, we'll write another number. Obviously it's not going to be prime because we've assumed there's no other primes. So we're going to write another number, which is the product of all 6 of the first prime numbers. Okay, so 2, 3, 5, 7, 11, 13. Okay, so we know that number that we've got, okay, so the number we've got, which is 2, 3, 5, 7, 11, 13, the product of those, which is 30,030, is definitely got 2, 3, 5, 7, 11, and 13 as its factors. It's got a factor of each of those. And in fact, there are 6 prime numbers that we're trying to prove. Now, what I'm going to do is just add 1 to this number. If I add just 1 to that number, what that does, it makes each of these numbers here now definitely not be able to divide into it. So just adding the number 1 stops the 2, the 3, the 5, the 7, 11, and 13 being able to divide it. You can try it yourself. Just get your calculator, try putting in 30,031, try dividing it by each of those. Each one of them will fail. Okay, each one of them will fail. So because you know that 30,031 doesn't divide into 2, 3, 5, 7, 11, or 13, it means it can either divide by 1 and itself, or some multiple of another number that we don't know, another prime number. Okay, and that's it then. We've proved by contradiction that there is more than 6 prime numbers. Okay, because we've proved that 30,031 is definitely going to be prime or have a prime number as one of its factors. Okay, so we just proved that there is more than 6 prime numbers. What we want to do now is extend that proof to show that there is an infinite amount of prime numbers. That the prime numbers just keep going on forever. All right, so we need to use that similar technique to what we just used with the proof by contradiction to show there is an infinite amount of primes. Now you need to learn this proof off by heart. You need to make sure that you understand it and are able to redo it ready for your exam. Exactly the same as when you did the square root of showing that root 2 is irrational earlier on. You need to learn this one off by heart as well. Okay, so let's have a quick look through then. It's exactly the same technique as what we just saw. So first thing we want to do is say if we want to prove there is an infinite amount of primes, I'm going to look at the contradiction of that and prove that there is a set number of prime numbers. Okay, that there is a finite amount of prime numbers out there, and they stop at a certain point. We don't know where that point is, but they definitely stop somewhere, and there is no more primes after that. That's what we're going to assume, and we want to show that's not true, and hence prove the original statement. So the proof requires we understand that it's expressed as a unique set. There is a set of prime numbers out there. We don't know what they are, and we need to show what they are. But what you need to do is you also need to understand this part of the statement here. And you saw this at GCSE. Every single number out there, every single number there is, has what we call a unique set of prime factors. It doesn't matter what number you have, you could write it in a set of prime factors. For example, the number 10. Number 10 has the prime factors 2 and 5. 2 times 5 is 10. No other number has just 2 and 5 as its prime factors. So every single number has always got a unique set of prime numbers. Exactly the same reason is 20. Don't forget you can use more than one lot of the prime number. So for example, 20, the only number, the only set of the prime factors of 20 is 2 times 2 times 5. Or sometimes you write it as 2 squared times 5. But there is no other number that has 2, 2, and 5 as its prime factors. Okay, right, so as long as you understand that, then you can start understanding this proof. So if I know that's true, and I'm going to assume the opposite now, I'm going to say it's not true. It means there's a finite number of primes out there, this set number of primes. So if I know that, what I can do is I can multiply all these primes together that I definitely know. All right, our finite number of primes. There's loads of them, but if I took the time, I could go through them 2, 3, 5, 7, blah 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 blah, up to this end point. And past that end point, there is no more prime numbers. Okay, so I'm going to do that. 2 times 8. It's going to be a massive number. So what I'll do is I'll just call it this constant A, right? This number A. Okay. Don't know what it is, don't really care, just I know that when I've multiplied these set number of primes together, I get this number A. Now the number A means that it's got 2, 3, 5, 7 and all the numbers as one of its factors. So if I just do this one technique that I just saw, by adding 1 to that number a, it can now not be divided by 2, it can't be divided by 3, it can't be divided by 5, and so on, all the way up to my last prime number, which I'm calling Pn in this case, the very last prime number. So just adding 1 to that product means it now can't be divided by any of these numbers. And the reason why is because it would have a remainder of 1. Okay, definitely. So what I can do then is that say that a plus 1, whatever number this is, does not have 2, 3, 5 up to all these prime numbers that I've said are the only prime numbers as its factor. Now if that's true, that means that it is either prime itself, so it's a prime number itself, or one of its factors is a prime number which we don't know. But what's important is that prime number we don't know is not in our unique list of prime numbers. And that's where you got the contradiction. So a plus 1 must have a prime factor or be a prime itself. So a plus 1 is not in this list of primes. And because it's not in this list of primes, therefore it contradicts this original statement just here, that there's a finite number of primes, and therefore. Okay, so just before you complete this exercise, what I would strongly recommend is you learn the 2 proofs, the proof of an infinite set of primes and the proof that root 2 is irrational. And what it's probably a good idea to do is just to close your notebook, have a go at proving those 2 things yourself again and see if you can remember how to do them. So although you've just written them in your notebooks, it would be a good idea for you to re-practice both of those so you fully understand how to do those proofs. Once you've done those proofs and you've learnt them off by heart, then it'd be a good idea to go on to the exercise 1.1 and practice some other proof by contradictions.